There are different techniques to analyze the behavior of nonlinear systems, and in today's lecture and in next few lectures we shall talk about phase plane analysis of nonlinear systems. We shall study what is phase portrait, and we shall learn how to plot phase portraits, and we shall also learn how to describe the behavior of nonlinear systems using phase portraits. So first question is what are phase portraits? So if you are provided with a second order nonlinear system, here you have the first state is x1, its derivative is some nonlinear function of states x1 and x2. Likewise, in the second equation, f2 is another nonlinear function of x1 and x2. Phase portrait is plot of trajectories in phase plane for various initial conditions. So here are some new words. First, what is trajectory? And secondly, what is phase plane? So what is trajectory of a system? So here x1 and x2, these are solutions to these two differential equations, and plot of x1 and x2 in this plane, x1 x2 plane, for a given initial condition, that is called trajectory. So plot of x1 and x2 in this plane, that is called trajectory of the system, where x1 and x2 are the solutions to these differential equations. And this plane, x1 x2 plane, that is called phase plane or phase state plane, right? Here x1 on the horizontal axis and x2 on the vertical axis. This plane is called phase plane. And plot of trajectories, system trajectories for different initial conditions in phase plane, that is called phase portrait. Phase portrait is basically a graphical technique to analyze the behavior of second order nonlinear system. It describes the qualitative behavior. Qualitative, what is difference between qualitative behavior and quantitative behavior? Right, it will not give you the exact numerical values. It will only tell you about the shape of the response, some qualitative properties of the response of the system. And advantage of this approach is that it can even handle hard nonlinearities. You learned that hard nonlinearities, they were difficult to linearize. We cannot linearize these nonlinearities. However, this phase portrait, phase plane analysis technique, that can also be utilized to analyze the behavior of nonlinear systems with hard nonlinearities. A limitation of this approach is that it is only limited to second order nonlinear systems. Just to describe these phase portraits, let's consider a second order system. It is equation which describes this mass and spring system, and this equation, it is in the same form as that was studied in previous slide. In this form, it can be brought it into this form. For example, by selection of this x1 to be equal to x and x2 equal to x dot, then these this equation, differential equation, can be brought into this form, which is similar to the one which we considered in the first slide. So for this system, phase portrait is given by this graph. Here on this horizontal axis we have x or x1, x and x1 are the same. On the vertical axis we have x dot and x2 are the same. So this is x1 x2 plane, which is the phase plane, and these are plot of x1 versus x2 for different initial condition. For one initial condition, for example, for this initial condition we had this graph. For another initial condition we had this graph, and for third initial condition we have this graph. So this graph is called phase portrait. How did we achieve it? There are different techniques. We shall study all those techniques in more details. Over here, since this system is simple, we can easily talk about the plot of phase portraits for this system. So how you can find expression for x1 and x2? You can easily solve this differential equation, second order differential equation. You know the procedure. The procedure is to first write the characteristic equation, determine the roots of this characteristic equation. Then what are solutions to this equation? So solution, if poles are purely imaginary, then we have this kind of solution. Where C1 and C2, what are these things? These are constants, can be determined by the initial conditions. So let's take this initial condition, that is x of 0 equal to x naught and x dot of 0 equal to 0. So for these initial conditions, what do we get? What is C1 and C2? For example, if we substitute x of 0 equal to x naught, so what is cos of 0? That is 1, and sine of 0 is 0. So then C1 comes out to be equal to x naught, and so this is a solution. X of t is equal to x naught cosine of t, and x dot of t, which is simply the derivative of this thing. And in the phase plane, phase portrait, we are interested in a relation between x and x dot, that is between x1 and x2. So how we can obtain a relation between x and x dot? We want to get rid of this time t. So how we can obtain a relation between x and x dot? Take square of this equation, and add the two. So cosine square t plus sine square t, what is that? That is 1. So by that thing, you will get rid of this time, and you will have a relation between x and x dot. So what is this equation? This is equation of a circle with center at origin and radius of circle equal to x naught. So initial condition. So these are circles with a different radius, and radius of this circle that depends upon the initial condition. So these are the phase portraits. We shall study in details how to how to sketch these phase portraits. Over here we had a simple system, and just to keep the continuity, I have described how to obtain phase portrait for this system. It can also be obtained using MATLAB. You already know how to implement this system in MATLAB and Simonic. You can simply implement it in MATLAB, and then use XY plotter in MATLAB with the x1 on the horizontal axis and x2 on the vertical axis. So this is the graph. So what information do we get from these phase portraits? Before, do you have a question? Okay. So before we talk about nonlinear systems, we study phase portraits for linear systems. And from the previous study, you know that qualitative behavior of linear systems can be easily described by eigenvalues of the system matrix. That you already know. So what is your observation? If eigenvalues are purely imaginary, what is shape of the response for that system? Oscillatory response. These are plot of the states for a given initial condition. And if eigenvalues of system matrix are complex, then what is qualitative behavior of the system? You have damped oscillations in that system. If you have eigenvalues which are real and equal, then this is the shape of response. And then you can have eigenvalues which are real and different, then you have overdamped response. This was critically damped and this is overdamped response. So qualitative behavior of linear systems can be easily described using eigenvalues. However, to study the qualitative behavior of nonlinear systems, we shall use phase portraits. Therefore, first we study the phase portraits of linear systems so that we can then generalize that concept to nonlinear systems. So now we can easily describe the qualitative behavior of linear systems by looking at eigenvalues. However, over here we are interested in studying the qualitative behavior of linear systems using phase portraits. So here we have a second order linear system, the corresponding characteristic equation and solution. What is solution to this second order differential equation? It is given in this form: if lambda 1 is not equal to lambda 2, and if lambda 1 is equal to lambda 2, then we have this solution. Is it clear? There are different possibilities for lambda 1 and lambda 2. For example, lambda 1 and lambda 2, they can be both real and have the same sign. Have the same sign means they can both have positive sign or both of them can have negative sign. The second possibility for lambda 1 and lambda 2 is that both of them are real and they have opposite sign, and then they are complex. They are complex, and if they are complex, then they exist in pair. That is, they are complex conjugate with non-zero real part, and this is fourth possibility. They are complex conjugate with zero real part. Corresponding to each situation, we draw phase portraits. If lambda 1 and lambda 2 are complex conjugate with non-zero real part, then what is qualitative behavior of the system from the linear control theory that you have already studied? You are right that there will be oscillations. Either these oscillations will be growing oscillations or decaying oscillations, depending upon the real part of these eigenvalues. If the real part of the eigenvalues is negative, then the response will be decaying oscillations. And uh, that is, if this is the situation, then this will be the shape of phase portrait. What is this thing? This is plot between x1 and x2, that is between x and x dot. So this situation, we are talking about this situation. So x1 and x2 both are plotted over here, and if we plot x1 versus x2, will be the shape of graph? So this will be the shape of graph. What you see is that, for example, if we talk about x, initially, for example, at this point x is positive, and then what happens to magnitude of x? Magnitude of x is decreasing, becomes 0. Magnitude of x becomes 0 over here, and then what happens to the magnitude of x? It becomes negative, and maximum in the negative direction, and then it again becomes 0, and then there is peak in positive direction. So it is same thing, decaying oscillations in x. And what about x dot? It is also oscillatory. So if we plot x1 versus x2 for this situation, we shall have this phase portrait. Is it clear? And if we have this situation, then we will have growing, this direction of this arrow is in the direction of increasing time. So this will be growing. Such kind of phase portrait, that is called focus. There are two possibilities. You can have stable focus, you can have unstable focus. So this is a phase portrait corresponding to this possibility. Let's talk about these possibilities. Lambda 1 and lambda 2 are real and have the same sign. So for same sign, what is qualitative behavior corresponding to this situation? Overdamped. So in that case, what is plot between x and x dot? The plot will look like this one. There is no oscillations. For example, if we talk about x, so what happens to the magnitude of x? Magnitude of x, there is no oscillations as we have seen it over here, this situation or this situation. So magnitude of x, there are no oscillations in its magnitude, and that is also shown in this graph. For stable case, trajectories finally converge to origin. For unstable case, trajectories grow to become unbounded. Is it clear? So this kind of phase portrait, that is node. We have two possibilities, stable node and unstable node. What is situation corresponding to this thing? Lambda 1 and lambda 2 are complex conjugate with zero real part. Oscillations, and this is the situation. What is phase portrait? Circles, as we have already sketched. So these are circles, and is such kind of phase portrait will be called center, right? And we are left with one more possibility, that is lambda 1 and lambda 2 are real and have opposite sign. So what will be situation over here? That is one eigenvalue is positive, one eigenvalue is negative. So what will be the plot of system trajectories? What is solution in this case? Solution, if uh, lambda 1 and lambda 2 are not equal, then this is solution. How we determine k1 and k2? How these are determined? These are determined from initial conditions. So depending upon the initial conditions, k1 and k2 can have different values. One of these exponential term is growing exponential and other is decaying exponential, right? Because one is negative and one is positive. So one exponential is decaying and other is growing exponential. So what will be overall response? One term decaying, another one growing. What is sum of the two? So the response will be growing response. जो decaying है वो, for example, it even if it becomes 0, then the term which is growing, that will always dominate. So in general, response will be unstable, that will be trajectories will become unbounded. There is one exception. These k1 and k2 are determined from initial condition. There will be one set of initial conditions for which k2 will be 0. The constant associated with growing exponential will be 0. There will be certain set of initial conditions corresponding to which k2 will be 0. In that case, what will be the situation? Trajectories will converge to the equilibrium point, that is at origin. So for all other initial conditions, trajectories will become unbounded. For certain initial conditions, the trajectories will converge to origin. So that is situation over here. I think it is visible. For certain initial condition, these are represented by these straight lines. For these set of initial conditions, trajectories are converging to origin. For all other initial conditions, for example, for this initial condition, the response grows to become unbounded. This arrow is in the direction of time. So as time passes, these trajectories will become unbounded. So such kind of phase portrait, that is called saddle. So now you are able to describe the qualitative behavior of linear systems by looking at their phase portraits. So even if you are not provided with the eigenvalues, all of you should be able to describe the qualitative behavior of linear systems looking at phase portraits. For example, if a phase portrait has this shape, then what will be the behavior of the system? decaying oscillations, and here again oscillatory response. However, the magnitude of oscillations is growing. What is this phase qualitative behavior corresponding to this phase portrait? It is decaying without oscillations, and this one is growing without oscillations. There is in these cases response is not oscillatory. Here the response is there will be sustained oscillations, and in this case the response will be practically will always be growing. However, theoretically or in simulations, it will converge to origin for certain set of initial conditions. For all other set of initial conditions, it will be growing. ठीक है, practically क्यों ये unstable होगा? Because in real systems there are always disturbances and uncertainties. Those will cause the trajectories to slightly move away from this straight line, from this line, and if it moves away from this line, and then the trajectories will become unbounded. So now you are able to describe the qualitative behavior of systems by looking at their phase portraits. For at least for linear systems, we can extend that knowledge to nonlinear systems as well. So let's describe the qualitative behavior of this pendulum using phase portraits. We are already familiar with the qualitative behavior of this equilibrium, this system, this pendulum. We know that this equilibrium point, which is at position 0, 0, that is stable equilibrium point. There will be oscillatory response in the system, and after oscillations it will settle down if there is some friction. What about the equilibrium point in upright position? That is unstable equilibrium point. Trajectories starting from that initial condition, that will be growing. So this is the equation. So we have determined we have taken some numerical values for these constants, and then these state equations are given over here. Equilibrium points can be easily determined by substituting all derivatives equal to 0, and these are the equilibrium points for this system, as we have already talked about. There are multiple equilibrium points, physically two distinct equilibrium points. Here is the phase portrait for this system for different initial conditions. How did we obtain this phase portrait? We shall talk about it later in more details. That is how to obtain phase portraits for nonlinear systems. Over here, we just want to describe the behavior of this system by looking at the phase portraits. So this is first equilibrium point, another equilibrium point, another equilibrium point. One equilibrium point at origin, another at pi and 0. And sorry, here is the second equilibrium point, which is at pi and 0. This is 2 pi 0, and this one is minus pi 0, minus 2 pi 0. I think in these phase portraits a friction term is also there. Friction term is also there. So what do you how do you describe the qualitative behavior of this system near this equilibrium point? For example, corresponding to this initial condition, what will be the behavior of this system? Or for example, corresponding to this initial condition, what is this initial condition? Velocity equal to 0, that x2 equal to 0 and x1 equal to some number between 0 and this is between pi, between 0 and pi. So for this initial condition, what will be the response of the system? It is stable focus. That is the trajectories will finally converge to origin after oscillations. That we already know from this because we already know this physical system. So even if you do not have the understanding, physical understanding of this system, you are now able to describe the qualitative behavior of this system near the equilibrium point. This equilibrium point is the same physically, the same as this one. Theoretically, it is something different. What is difference between the two? For example, if you have this initial condition, this one over here, it means very high velocity and position equal to 0. That is, position was 0 and angular position is 0, but it was moving with very high velocity. So what will be the situation? It will again converge to this equilibrium point after oscillations. This equilibrium point is physically the same as this one. The difference is that before reaching to this downward position, there will be one complete rotation in the pendulum, right? 2 pi. That is, it was initially, this pendulum was initially at this position. There was high velocity, and due to that velocity, it rotated and finally then oscillated about this equilibrium point, right? So this is a difference between this equilibrium point and this one. Is it clear? What is the behavior of the system corresponding to, for example, this initial condition? This initial condition. ये वाला equilibrium point, what is behavior of this equilibrium point? Saddle, right? It is saddle. It is saddle. That is corresponding to certain initial conditions, certain set of initial conditions. The trajectories, for example, corresponding to this initial condition, the trajectories will finally reach at this equilibrium point. What is this equilibrium point physically? Upright position. For all other initial conditions, the trajectories will either converge to this equilibrium point or to this one, right? And the other equilibrium point. So for certain initial conditions which lie on this line and on this line, the trajectories converge to this equilibrium point. For all other initial conditions, this trajectories will converge to some other equilibrium points. This is theoretically. Practically, of course, it will not be stable because of disturbances. However, in ideal case, when there is no disturbance, everything is perfect. If you give this velocity to this pendulum, and with this particular velocity, it will rotate to finally become stable at upright position, right? Meaning of this trajectory is this one. So, is it clear? We shall talk about the qualitative behavior of nonlinear systems in more details using phase portraits, and then in the next lectures we shall also learn how to plot these phase portraits.